So we have discussed the mechanical energies in the last term. The two types of mechanical energies are kinetic energy and the potential energy. We'll study the kinetic energy and potential energy in detail one by one, and in this process we are starting with the kinetic energy. If we talk about the cannonball which is fired by a cannon, then because of its kinetic energy, it is able to break the walls of great forts. After hitting it, it can make the wall on the ground. So we know that every object which is in motion possesses some energy by which it can do some work. For an example, all we know that the water dams are constructed in order to get the energy through the flowing water. When the water is stored in the reservoir behind the dam, when the gates are opened and the water starts to flow, by the flowing water we can rotate the turbines and can get the hydroelectricity. So all we know that a moving object can perform some work. Now, the energy which is due to the motion of any object is said to be kinetic energy. Let us derive the expression for the kinetic energy. Ke is the abbreviation I am using here for the kinetic energy. Now, let us have a body which is initially moving with the constant speed v0. Now, we observe that a force is applied in the direction of motion of the object, and due to the force application, the acceleration occurs in the object and its velocity increases. And after a while, or we can say that after the displacement s, this object acquires the new velocity which is v. Now, here it is given that the mass of the object is small m. Its initial velocity is v0. Its final velocity, which is acquired by applying the force which makes it displace by distance s, and the final velocity is acquired which is small v. Now, as we know that the displacement under the force is equal to s, then by applying the third equation of motion, which all you know, connects the final velocity with initial velocity, and the acceleration produced which makes the body displaced by the displacement s. This equation says that v square should be equivalent to u square plus 2as. Now, here we know that final velocity square is equal to initial velocity, which in our case is v naught square, plus 2 into a into s. Now here we can write this equation as follows. Final velocity square minus initial velocity square upon 2a is equivalent to s. As we know that the work done by the force under this process can be written as F into S, as force is equivalent to mass into acceleration into S. That's why we can write as that the work done on the object, which is here W, should be the change in kinetic energy occurred in the object. For the object, the change in kinetic energy can be represented by delta K, and hence we can see that mass into acceleration into displacement should be equivalent to this change in kinetic energy. If we put the value of A into S, see, in this equation we can write it as AS is equivalent to V square minus V naught square upon 2. If we use this value in this equation, then we can get the change in kinetic energy as half into m V square minus V naught square. So this is the change in kinetic energy. That implies that change in kinetic energy, which should be K final minus K initial, should be equivalent to half m final velocity square minus half m initial velocity square. So when we come to the point that if the initial velocity of the object was 0 meter per second and the final velocity was v, then the change in kinetic energy or the kinetic energy value acquired by the object at the final reference, then it will be half into m v square minus 0. That's why the expression for kinetic energy when the object starts from the rest can be given as half m v square. So mathematically the kinetic energy is also defined as that it is the half value of the product of mass and square of the velocity. See, as the kinetic energy is form of energy, hence it is scalar in nature. SI unit is joule, CGS unit is arc, it is given as half into m into v vector dot v vector, which gives us the value half mv square, which is not responding to the direction of the motion of the object. Relation between the momentum and the kinetic energy. For an object of mass m velocity v, the kinetic energy can be written as half into m into v square. Now, if we multiply this fraction by m and divide it by m2, then there will be no effect on the value. So we are doing it that we can get a relationship between the kinetic energy and the momentum. So we observe that it becomes 1 by 2m into mv whole square. Now if we change it with the momentum expression, then we'll have the new value, which is kinetic energy is equivalent to half of m into v square, as well as in terms of momentum, kinetic energy is equals to momentum square upon 2m. So these are the two expressions for the kinetic energy. Now we have equations, numericals to solve out. In the question we are given that the momentum of an object is increased by 5%. The final momentum is increased by the 5% value of the initial one. That is, it will be equivalent to 1 by 20 of initial value. This is the equation 1. Now, we have asked for the change in kinetic energy. So, let's see if the kinetic energy initial was equivalent to pi square upon 2m, then the final kinetic energy will be 21 by 20 whole square pi upon 2m. This is the equation 3. Now let's see what is the change in kinetic energy. The change in kinetic energy will be kf minus ki is equivalent to 21 by 20, that's whole square, pi square upon 2m minus pi square upon 2m. Now, as we have to calculate the percentage change in kinetic energy, so we should write delta k upon ki into 100, that is the percentage change. Now, here kf minus ki upon ki into 100, and which is equal to 41 upon 400 ki minus 400 ki. If the LCM is taken, then it will be like this. 100. Here will be get the value in percentage. So as we solve the numerator, it will be 41 ki upon 400, and with the 100 will be having the 41 upon 4, and this value comes equal to 10.25%. So this is the percentage change occurred in the kinetic energy. As this is positive, that means the kinetic energy is increased, and we know as per the relation between the kinetic energy and the momentum that it is proportional to the square of momentum if mass is constant.